Over the past century, by delving into the infinitely small, we have discovered a type of reality as insane as a sleepless chicken on an lysergic acid diethylamide trip. And the thoughts of the physicists who were the first to study this part of the universe could be summed up in 4 words. What the hell is this? It must be said that the explosive cocktail of events, each more counterintuitive than the last, that we found there is enough to blow your mind. Just consider this. In the infinitely small, things can be in several places at once. Observing an experiment can change its outcome. The concepts of position, object, and time are shattered there. And even though so-called quantum physics, developed by researchers who spent their lives studying its rules and laws, is able to describe and predict the behavior of matter. In the infinitely small, with an astonishing level of precision, to be honest, no one really understands it. Well, no one knows exactly what these discoveries tell us about the nature of reality. Faced with this frustrating realization, some of our greatest minds started proposing interpretations for these bizarre experiments. I'd rather warn you right away. This journey, which will take you to climb some structures, is not without risk for your brain. A lot of what follows may even seem hard for you to accept. We're going to see landscapes that get crazier and more bewildering each time. Or sometimes, just opening a simple box is enough to trigger a whole new universe. But what I can promise you is that, as rope partners, we'll fall and get back up together. And once we reach the top of this wild journey, the view will be as magnificent as it is dizzying. And with that, let's get back to our topic, which will slowly start to climb, making sure to lay some solid foundations. Thanks to the amazing experience of the double slit experiment, which alone captures all the strangeness of the infinitely small. If you already know it, it's a chance to refresh your memory while getting your brain working. On paper, this experiment couldn't be simpler. You have a source that can send light or quantum particles, such as electrons, toward a plate with 2 vertical slits. And behind this plate, a screen has been placed, a wall that allows us to record the position of the impacts, the exact spot where the particles will hit. If your source is a laser, then the light wave passes through both slits at the same time. And once it passes through, it splits into 2 secondary waves that start to interfere with each other. Like the bottom of waves that meet on the surface of a lake, where the crests and troughs reinforce or cancel each other out, depending on how they cross. So a strange pattern appears on the screen. A kind of psychedelic barcode, made up of alternating light and dark bands. So far, nothing too disturbing. These interference patterns simply show us the wave nature of light. Enjoy this moment. It might be the only one that seems logical and coherent to you for a while. Because now, if we perform the same experiment, but instead of sending rays of light with a laser, we shoot particles such as electrons, then the world is going to tip into the strange. Already we can anticipate what we expect to find. We agree that if we shoot at this wall with 2 slits using a machine gun firing small pellets, we should observe on the other side impact points distributed more or less randomly depending on the shooting angles. Except that's absolutely not what we observe at the scale of the infinitely small, because as more and more electrons come one after another crashing into the wall, things start to get really weird. Because their impacts will gradually draw the same interference pattern that we get with light. Even though we sent one after another particles that are truly material, that have mass. Which means that each electron throughout its journey behaved like a wave, which passed through both slits at the same time, split to interfere with itself along the way, and upon hitting the wall, turned back into a particle. I'm saying it again for you, but also a lot for myself. The electrons were sent one by one, and yet each of them behaved like a wave and went through both slits at the same time before interfering with itself. In the end, it crashed into the wall as a particle at a very specific spot. And this is where things get even stranger. If we try to determine which path each electron takes, and if we set up a small detector at the slits to find out which one it goes through, then, as if by magic, we clearly see electrons pass through either slit. And on the final screen, the interference pattern disappears. As if trying to find out which path the electrons take forces them to behave like particles. As if simply observing the world forced it to make a decision. And that's a real bombshell. In the infinitely small, simply observing changes the final result of the experiment. Asking a question changes the answer. Honestly, even though I'm familiar with the result of this experiment, every time I dive back into it, my common sense just breaks down. And now, I guess that, like me, you can't help but wonder which slit the electron actually goes through in the end. Well, the answer to that question is that it's not the right question. The electron doesn't go through one slit or the other, or both. At the same time, it simultaneously explores all the paths it could potentially take. And the path it ultimately takes depends on what we choose to observe. At the scale of the infinitely small, as long as we don't look at it, the universe explores all possible options, but as soon as we observe it, it seems to choose. We don't just discover things, we create what exists. By intervening, rest assured, it's completely normal if you have a headache and your brain is screaming at you to reject the result of this experiment. The reverse would be concerning. Most physicists find it easier to face an octopus in a tap dancing contest than to grasp the deeper meanings of the phenomena revealed by this experiment. Because this touches the heart of the oddities that reign supreme in the realm of the infinitely small. In the macroscopic world in which we live, objects can only take one path at a time. At the quantum scale, things differ. A particle, something we usually imagine as having a material consistency and a precise position, can take several paths at the same time. Behaving like a wave and like a particle, let's be honest, that's still hard to grasp. Yet this experiment has been repeated thousands of times with photons, electrons, atoms, and even under very well-controlled conditions, with molecules made up of hundreds of atoms. Each time the same thing happens. Physicists have had to admit it exists, a world made of objects that are impossible to track and can only be described as waves of probability of presence. A world of objects that do not pre-exist our gaze, but are constructed with it. Quantum physics is like a magic trick where it's the hat that chooses what you'll find in it at the moment you look inside. Let's summarize the main shocks from this experiment. The electron, like all other particles, doesn't behave like tiny balls with a clear position and speed, but rather like wave functions. Clouds of probabilities, bubbles of fog, and possibilities within which matter is in a superposition of states, here and there at the same time. And when we try to look at it, to measure it, the wave function collapses and the electron goes from diffuse clouds of probabilities to an extremely well-localized point. In other words, trying to track down matter is like playing hide and seek with a player who doesn't exist until you find him. I feel like it's a bit confusing for you right now. Don't leave, don't give up, you're going to see it's fascinating, and if I do a decent job. Once certain ideas are accepted, they should settle in your mind, plant anticipation, and stay there for quite a while. In fact, it's as if on a very small scale, reality is a kind of perpetual rough draft. Until interaction with other elements of reality pushes it to publish a paragraph, to choose a version of the story. The next obstacle to overcome in our ascent is quantum entanglement. A property of matter that has made many physicists eat their hats with their own toothy heads. If you take two particles such as electrons and make them interact, you can entangle them. That is, make them enter into a kind of quantum pact that forces them to share a common state. And what's really disturbing is that if these two entangled particles are sent in opposite directions, then even if they're thousands of kilometers apart from each other, they maintain an instantaneous correlation. If you measure one, the other knows it and behaves accordingly, instantly. Not a few moments later, not the time it would take for some hypothetical information to connect them, but instantly. Einstein, who indirectly contributed to this discovery, didn't like this idea of instant action at a distance at all, because it seems to violate this rule of Aaron that tells us that in our universe, nothing can move faster than light does in a vacuum. But this strange phenomenon of quantum entanglement doesn't contradict relativity, because no message is being transmitted. What we observe is that two quantum particles can form a single system, a single object, even if they are separated by immense distances. I'm going to sit down for a bit. Quantum physics is when the future, the past, and intention intersect in a waiting room that doesn't exist yet. Even more disturbing, we've developed a version of the double slit experiment, which seems to be as much a time machine as it is a brain teaser. In this so-called delayed choice experiment, the principle is to turn on the detector, trying to see which slit the electron passes through after the wave has gone through both slits. And where it gets really crazy is that the fact of choosing whether or not to observe the place where the wave has already passed will change its behavior. After the fact, the wave has already passed through both slits when we try to find out which one it went through. And then it rewrites its own past depending on what we decide to know in its present. In other words, at the scale of the infinitely small, what you do now can influence what happened before. The past isn't fixed in reality. It often feels like it waits for us to observe before deciding, and we agree. It's as easy to imagine as an intellectual gymnastics exercise, where one of the required moves would be to land with both feet together inside your own skull. It's just as crazy and counterintuitive as it sounds. In our world, the past shapes the present, and your decision to have lunch today doesn't change what you ate yesterday. But in the quantum world, it's as if a fruit juice might not have any taste until you drink it. And once you touch it to your lips, it can change its fruit. What this experiment tells us is that in the infinitely small, time is not a straight line with a preferred direction. And the future is not a consequence of the past, because causes do not always precede effects. There's an even more extreme version of this experiment, a devilish cousin. By showing that if we don't directly measure which slit the particle went through, but instead make it leave a trace of its passage. A kind of trace stored in a secondary system. Then, the behavior of the electrons along the path and the patterns that we will see appear on the wall will depend on what we do, on the stored information that we haven't yet chosen to look at. If this information about the path taken remains accessible, there is no interference. And if we decide to erase the information after the electrons have passed, the interference pattern reappears. It's as if the universe is telling us, as long as you haven't looked at the investigation report, the crime hasn't happened yet. Quantum behavior adapts afterwards depending on what we choose. Not to know. I'm going to sit down again. Since the result of this experiment is harder to swallow than a brick, I'll give you a second to digest it. One more, if you want. Science doesn't break the magic, it reveals it. And here, we need to insist on something that's often hard to accept. Quantum physics, the science that describes the behavior of things in the realm of the infinitely small, doesn't tell us that our knowledge is incomplete or approximate. It doesn't say this world is crazy, but that it's fundamentally blurry. Even with the wisdom of Einstein and Yoda, combined with the power of all the computers in the world, you couldn't predict exactly where an electron is before you've observed it. And that's not a flaw in our knowledge or in the system, it's the system itself telling us. Here is a rule that governs me. I am a mixture of chance and apparent madness. At my level, the behavior of particles is fundamentally uncertain. All options are on the table with me. Until your measurement brings down the curtain of probability by forcing the wave function to collapse, freezing the blur into a single position. quantum physics is like a box of chocolates. You never know exactly what you're going to get. If you're attached to logic, you might feel it starting to itch. On one hand, we have quantum mechanics, whose equations describe with almost outrageous precision the wacky behavior of matter. At very small scales, they've allowed us to develop lasers, MRIs, transistors, and computers. And on the other side of this extremely effective science, which is surely one of the most precise models ever conceived by human intelligence, there's a lingering sense of incompleteness. A tiny detail, a very small problem, the kind that keeps you from falling asleep. The elephant on steroids in a porcelain matchbox. The thing is, quantum physics tells us nothing. Deep reasons why reality behaves in such a bewildering way. We can make particles move to the rhythm of uncertainties we control, but we don't know why they follow these strange rules. What happens during the collapse? Why do particles choose one path over another? And do they really choose anything at all? What does reality look like? When we don't try to observe it, are particles anything before we measure them? And does the observer really change reality, or does he just reveal it? To all these dizzying questions, quantum mechanics remains silent. It is a remarkably effective compass for finding our way on the map of possible paths, but it tells us nothing about the landscapes we cross. It's a science that predicts without knowing what it observes. It only tells us about the part of reality that is willing to reveal itself at a given moment, T, and which depends on the question we ask it. Admit that it's philosophically explosive. It's a bit like you're piloting a highly sophisticated ship with an engine precisely wired by you and purring perfectly without knowing exactly what fuel it uses. And it's because they're frustrated by this symphony that plays us a perfect score without being able to tell us anything. The instruments that do it, physicists like us who want to understand reality, began seriously examining the machine's inner workings, to try to find meaning in it, to add a story to these laws without images. Okay, we're almost at the top, and to get there are about 10 different ways today. Major possible interpretations of quantum physics, all competing with each other. And each of these different scenarios turns the brain upside down in its own way. I won't detail them all, as some are very technical. I'll share with you the ones that are most discussed and that I think you and I can manage to understand. Let's start with the Copenhagen interpretation, which is kind of the one that avoids the headache and basically tells us that at the scale of the infinitely small, things don't have defined properties before we measure them. That's just how it is. Get used to it. As long as nothing is measured, the world is blurry, filled with superpositions, probabilities, and parallel states. And then, when we observe it, one reality is chosen. An indecision turns into a clear result. Period. Move on and you'll sleep better. Because the conceptual barrier between the quantum world and the classical world is impossible to cross. This interpretation could be summed up as, don't ask questions, do the math, it works, that's already amazing. Some see it as silent pragmatism, others as a refusal to face obstacles. What happens to reality when it isn't observed? Well, nothing. What quantum entities like electrons do between measurements isn't mysterious, it's just an invalid question. Reality may not be the permanent background of the world, but an event between two silences. What happens when an interaction makes it appear? The Copenhagen interpretation is the one that agrees to read a good detective novel, which at no point will give you the culprit. However, for many researchers, that's insufficient. Falling asleep isn't the main issue. He is frustrated by the idea that reality is suspended between two measurements, in an indeterminate state where all possibilities exist in potential, until we look, as Schrödinger proposed in 1935. A thought experiment that killed a staggering number of cats and made the neurons of several generations of physicists grind, by showing just how absolutely absurd all this becomes when you push the logic to its limit. Schrödinger's cat thought experiment consists of imagining a cat locked in a box, isolated from any interference with the outside world. And inside the box is a device containing a quantum particle that every 10 minutes has a 50-50 chance of changing its state, and to trigger a mechanism that will drop a hammer onto a vial of poison, almost instantly killing the cat. Now, if we close this box, Schrödinger tells us that if we strictly follow the rules of quantum mechanics, as long as we haven't reopened it, the wave function of the isolated particle hasn't collapsed and it remains superposed between two states. The mechanism has been triggered, yet remains inactive at the same time. The hammer has both fallen and is still hanging, and the poison is both released and still in its vial, and the living cat is dead at the same time. It's not that we don't know, it is literally alive and dead at the same time. What Schrödinger wanted to show with his thought experiment is that if you accept that a particle can have two states, then, by necessity, you must also accept that a living being, like a cat, can also be in two states. Which, let's admit it, is rather disturbing. One way to resolve this paradox is to imagine that both possibilities have occurred separately, in different universes. In one universe, the box was opened and the cat was alive. In the other, it was dead. Both possible destinies actually exist, but in two different realities. The many worlds interpretation, proposed by physicist Hugh Everett, was just one letter away from Everest. It proposes that whenever a quantum event has several outcomes, all of them happen. The universe splits into countless variants. As if the world were a novel with endless branches, its reading decided the outcome. Which chapters become real in the universe we experience? And the apparent randomness we observe in the quantum world is just a reflection of our position in a branching multiverse. According to this disconcerting interpretation, wave functions never really collapse. They split the universe into as many branches as there are possibilities, and where other scenarios beyond those we experience occur. All possible alternatives to those that exist here are indeed realized, but in distinct universes, different branches of this unbridled multiverse, which are all as real as ours, but inaccessible. If this dizzying hypothesis makes you a little uncomfortable, you can reassure yourself by remembering that if this interpretation is correct, then there is a version of you who never got into this video or disconnected before this moment, and who will sleep tonight with one eye open. Now let's put the multiverses aside and try to save our sleep by diving into the de Broglie-Bohm interpretation. It's much easier to digest, since it doesn't assume the existence of other universes besides our own. To put it simply, according to this interpretation, there are hidden variables that are currently inaccessible to our measuring tools, which would determine everything we observe. Here, particles really exist and have clear and precise trajectories. An invisible pilot wave imposes these on them, guiding their movements and connecting them instantly. Despite the distance between them, all elements of the universe are interconnected. If the path of the particles, is it only because it appears that way to us? Like surfers that we would see moving forward without seeing the waves that support them and allow them to advance, and which for their part have a very predictable behavior. Basically, the idea is that there is a discrete and even deeper level of reality, which is still mysterious to us for now. In the de Broglie-Bohm interpretation, the superposition of piles is just a lack of knowledge, and the cat is either alive or dead, but we don't know it yet. Finally, there's the relational interpretation, which tells us that reality is not a thing or a place, but a process, a relationship. According to this, matter and particles cannot exist independently. They only appear in interaction. There is no absolute reality, only existences in relation to others. It's impossible to know if one day we'll be able to decide between all these possible interpretations about the nature of reality. But one thing is certain. We live in a world where every atom around us and within us obeys the rules of a game whose script no one truly understands. That doesn't stop the show from going on. Here we are at the top, and the dizziness can be felt from all sides. Whichever interpretation you prefer, you're facing a landscape that's both sublime and blurry, created by a crazy reality that has outpaced our imagination by staying one step ahead. That's where the real wonder begins, the realization that the universe may be at its foundations, so radically strange that it will remain forever inaccessible. For our modest brains, which have evolved to be efficient in the art of not dying and reproducing, and not to grasp the subtleties of a matter whose behavior defies understanding, and which the physicist Arthur Eddington beautifully summarized in this quote, "You cannot weave familiar concepts around the electron, an unknown thing made of something we can't identify." This theory doesn't seem particularly enlightening. I've read something like this elsewhere, the Sliktu Etov, about the Loindre Giré and Vrible. Mathematically robust, experimentally unassailable, and philosophically elusive, quantum mechanics reminds us that the universe is not here to be intelligible. Discovering something extraordinarily bizarre can feel like a nightmare for Cartesian minds. But it's also wonderful to imagine that matter is not something fixed, and that sometimes reality is too complicated to picture. In this sense, accepting to give up a clear image of the world is not an admission of ignorance, but a recognition of the fact that the very structure of reality may, in essence, be inaccessible to our senses. To continue to gain perspective and appreciate these landscapes at their true value, we would need to know how to speak the language of their inhabitants, mathematics, whose abstraction is perhaps the only way to access these phenomena that are so far removed from our common senses. But having at our disposal as our only weapon words that have long since shattered, about the immense strangeness of these little things that we have dared to tackle together, I am going to stop at this point and simply contemplate the landscape in your company.